here. We currently have 2 questions. One of them, unfortunately, I'm not able to answer. I'm not really able to compare Galapagos, goat, and octopus. I'm not an expert on those, so I apologize. The other question here we have is this one. Whether I can explain or create some symmetrical geometry, and we are going to do that. It's quite a long thing if you want to do it properly, so it will take about half an hour, but we still have some time to do some other things. So please post here in the Facebook event, which is called Research Grasshopper Free Broadcast. Post your question or do it immediately into the chat. I will see it right here, and we can start in a couple of minutes. Okay, I think it's time to start. So the question asked here, and I don't really know where. I need to find it. Was this? So can we make symmetrical shapes just like found on the Grasshopper forum? One of these. Hello, Ramsey. Yes, maybe, but I need to understand it a bit better. So you need to specify your question about form finding and anemone a bit better. I think I can. Anemone is very close to what I do. So if you can, in more details, I think we can do something. So now we are going to do something that looks like this, or maybe like this, or maybe like this one. So I think this one is probably the best of these three, but I will go through all the details and I will explain how these can be done in a proper way. First with the NURBS geometry and then with the mesh geometry. There should be another question here. There is one more question, so I will read it now. So I have a list of X numbers, and then I want to divide it into randomly lists with M and OP elements. And if M plus N plus O plus P not equal to X, it will create a list with the rest. Example, one list with 20 numbers and divide it to list A with 4 numbers, list B with 2 numbers, list C with 9 numbers, and list E with the rest. In this case, do you think coding is more efficient than to use the Grasshopper components? Okay, this is a very simple question. Let's start with that one. The lists and the data trees are always an issue with the Grasshopper, and there is not enough components to use them properly. But I think this one can be done pretty easily. So if you go to the sets, and I will create a list of anything. So I will create a list of 100 elements. So this is a series like that. So you see I've got 100 numbers here. So, or let's do the example, just like requested 20 values in a list. And then you want to divide it into more lists. So the first list should be 4 numbers, the second one 2 numbers, and so on, 9 numbers. So what you can do if you go to the sets here, you can, there is something called split list or partition list. So let's use the partition list, and this one requests the size of the partitions. So this is the list that we are partitioning, and then I will create a panel with a list of partition sizes. So the first size should be 4. If you are using panel to specify a list of values, now this is a list of values, you need to deselect multi-line data, which means if this is on by default, the data that you're entering, if I do this is one piece of data because it can be multi-line. So that's one piece of data in multiple lines. If I switch it off, then each new line is a new piece of data. So if I plug this here, then we end up having a couple of lists here. The first one contains 4 items. Now the second one contains 2 items. The third one contains 6 items. And this keeps repeating. If you don't want this repetition to happen, I don't think you can do it in a simple way, but you can calculate it manually. So if you want to have the rest in the last one, in the last list, then you can use a component called mass addition, which basically takes a list as an input and adds these numbers together. So in our case, this is going to be 12 because 4 plus 2 plus 6 is 12. So yes, there is 12. And then I can measure how long the original list is. So list length, which is 20. Subtract this number from 20. So this is the rest. So now I know that the last piece of data should be, last sublist should have 8 items. Therefore, I will take this as my given length of lists, and then I will merge it with the calculated one. So I will merge it with this number 8, and I end up having, for some reason I need to flatten here, because for some reason it is grafted, but this happens sometimes. Anyway, so I end up having a list of lengths, out of which the first X numbers are defined and the last one is calculated. So I use this for partitioning, and you see that I have 4 sublists. Now, if I make more items here, the last sublist is going to be longer. If you don't like it this way, end up having a data tree, which actually you should like, because data tree is always more efficient than anything else. But if you don't, then you can explode the data tree. So the component is called bang, explode tree, bang. And this, you can keep adding outputs here, and it will create separate lists. So now this is the first list, second list, and so on. So you end up having separate lists. But I still recommend keeping the data tree as it was before. So I hope this is answering your question. I'm giving you a like. Just let me know if this is fine. We can get back to it later on. I will save this that you can then have a look at that. Broadcast 01. Okay, let's work with the symmetry now. So I will start a new Grasshopper document and an empty Rhino file. So let's start with the simplest symmetry that I can imagine. I will just create any NURBS geometry. So this is my 0, 0. This is the X direction. This is the Y direction. And I will just draw some shape here. This is there's a surface. I will rebuild it so that I have more handles, more controls. I will switch on the control points. Now I will change its shape somehow, slightly. To see it better, I will switch on the rendering options so that we have it shaded. I will just change the shape slightly, like this, maybe even here. And then I will take this one and put it here, like that. So this is the shape that I want to mirror or have symmetrical. Now I need to specify the axis of symmetry, and in Grasshopper it's not an axis, it's always a symmetrical plane because we are working at 3 dimensions. So if you remember, if you imagine a mirror, the mirror is always a plane. So I will take this geometry as a brep or anything else into Grasshopper. It's like this. I will just hide the geometry here in Rhino. So I just created a new layer and switched off the original one, and I'll make it look a bit nicer. So this is the geometry that I want to mirror. Now there is a component called mirror, this one, and it requires the geometry that we are mirroring and the plane. By default, that's this plane that goes through the y-axis and upwards, and I end up having a mirrored geometry. Now this would be fine if only this wasn't just overlapping two geometries. Now we can, I would just change it a bit so that you see the problem there better than now, because now it looks so. You see it's overlapping in a way that you might not like. I will switch it off again, like that. So what we would manually do, I will just bake it for a moment. I will switch off my Grasshopper. What I would do is I would just trim this by this. Oh, sorry. Trim this out, and then I will trim this out. And this is what I want to end up having. But let's do it automatically in Grasshopper. So let's go back. I've got it there, right? Also, we can specify the mirroring plane. By default, it's world YZ. So let's do that YZ plane. That's the default one. And maybe we can just put a point here that will define the origin. So we'll refer a point. Now here, I'm changing the mirroring position. And also maybe I want to rotate it. So rotate 3D. So I can rotate, because rotating a plane doesn't really make any sense because it's rotating around its normal, and the normal is always the same for all the rotations. Basically, if you rotate a mirror, the image in the mirror doesn't rotate. So rotating a plane doesn't make any sense, but rotating an object in 3 dimensions, that already makes some sense. But we only want to rotate it around the world x-axis and around the world y-axis. Actually, not really world, but its own origin. So we want to rotate it around its own this axis and this axis. So let's deconstruct the plane. and we are rotating the plane around the x-axis, which is the x input, and this is the angle. So let's create a slider like that. Now I can rotate it this way. The origin, the rotation origin is the plane origin, so now I'm rotating it like this. And I want to rotate again the rotated one. So this one I want to rotate around the y-axis, and the origin remains the same. So I can hide these, and I can rotate the plane now in this direction and also in this direction. And that would be my mirroring plane. So this is probably too much, but let's go back slightly. We can mirror around this. So now this is quite a nice, and let's create the mirroring effect properly. So now we have the original object, which is this one. What I want to do logically, I want to split the object into two parts. I want to decide which one I want to keep, and only that one I will mirror, and then I can join them. I can actually weld them, and they become one object. So let's do that. First, I need to split a B-rep with a plane. I always keep forgetting where that is. B-rep. I want to find a plane and B-rep plane. This is the one. This is B-rep plane. That probably only finds a section, so that's not really what I want to have. So let's see if split actually works. Split B-rep to split, cutting shape. So let's give it a try. So I will take the original B-rep, which is this one, and I want to cut it with that plane. Let's see what happens, and it doesn't seem to be very happy. So this should be a cutter, which is a cutting shape. So let's see if we create a section like this, which actually creates a curve, that is a section curve between the plane and the B-rep, which is this one. It looks like this. And now let's use this one to split the B-rep. Well, that doesn't work. So basically what it wants, it also again wants another B-rep, which is not a bad idea because we are going to need one anyway. So yeah, trim solid also would somehow work, but nevertheless, what I want to do is I want to create a bounding box, a box that contains the whole B-rep, but I want the bounding box to be aligned to this plane that I have here. So bounding box, which is this one. I will take the geometry, which is this one, and then I can specify the plane on which it should sit. So now this is the plane, and the whole object is inside of that bounding box. Now this is not working so well because you see that my splitting plane is somewhere inside, but the box is aligned. What does this mean? If we deconstruct box, this one, then you see that the dimensions of the box, mainly I'm interested in the z dimension, which is the one that is defined by the normal. So the box actually exists on this plane, and it has certain coordinates. So the x coordinate is defined by the x-axis, and it goes from here, which is minus something, to here, which is plus something. The y coordinate goes from actually plus something to even more plus something. And the z coordinate goes from minus something to plus something, or maybe the other way around. I'm not really sure. But just looking at that, it seems that this is the minus and this is the plus. And if I deconstruct the box, it gives me the domains of the box in the plane that I have here. So let's see if this is the aligned box. Yes. So I know that this distance from the 0 in the z direction should be minus 38.5. So I will now take the box, take this domain. I will deconstruct domain. I will take the start, or the smaller of those, but it's usually the start. So this should be minus 38. And I will move the box in the direction, actually the z direction of this plane. So I will deconstruct plane. I will take the z vector of this plane. I will set the amplitude to not minus 38 because I want to move it to the plane. I want to align it to the plane, so I need to plus 38, so negative value. This one, plug it here. And now let's see if this works. I will take the box and I will move it along this vector. And now it should perfectly sit on that plane, and it looks like it does. So now we have a box that should contain the geometry. It's only slightly shifted so that we are cutting the geometry at the position of this plane. Now, if we want to split something, so we want to actually split the geometry, we need to specify a cutting shape, which actually is this bounding box. So let's see what happens now. And you see that I ended up having two shapes here. One is here, and there is a cut here, which is defined by the bounding box, which is in turn defined by the plane, like that. This is good. And we end up having two shapes here, two B-reps. And I don't know which one is the one that I want to use, because it could be the first one, it could be the second one. So maybe I can ask whether something is in something, but the easiest thing would be to take 1 point from each of these planes and ask whether that point is inside of the bounding box. So I think it's in the vertex point in shape, not really, point in curve, contain, not really. So I think it should be somewhere here. I forgot precisely, point in B rep. So point in B rep. This one tells me whether a certain point is inside of a certain B rep. I'm curious whether points from these two shapes are inside of this B rep. So I will do this. I will now, I need to evaluate the surfaces, which is, evaluate surface, I misspelled. Evaluate surface. It requires a surface and a UV coordinate where I want to evaluate. And I want to evaluate in the very middle of each of these remaining shapes, because I need to make sure that, that my point is going to be certainly inside of the bounding box. So not on the side, not on the edge. So I will take graph mapper, multidimensional slider MD, which basically puts a point somewhere. So to make sure that 0505 is in the middle of a surface, I need to here reparameterize the surfaces. And I end up having 2 points. And these points, let's see the points. So now this is 1 point, and there should also be another point. Okay, that's strange a bit, because it only gives me 1 point. That's weird. But there are 2, and both of them are at the same point. That must be because I am. Let's rebuild it, because these 2 split surfaces, they're trimmed surfaces, so they still have the UV coordinates of the original one. So just to make sure that everything is actually working well. I need to rebuild the surface, or maybe basically the only thing that we need to find out whether some point from this surface or which surface has points inside of this bounding box. And the problem here is that if I evaluate each of these surfaces at their middle, the middle would be the same point because they are still same surfaces, just trimmed differently. So I could either rebuild those surfaces so that they lose the original idea of what they were, or I can do it some other way. So let's do it some other way because we don't care that much. Let's just take BREP edges, which is this one, and it extracts the edges. So I've got 4 edges in one branch, 4 edges in another branch, and that's fine. I will find discontinuities here, which gives me the points. Now I have a lot of points here. Now this is a bit unnecessary, but nevertheless, I just want to find a middle in this area, a center in this area. So we can try to join the curves so it creates one curve in each branch, and then we can measure the area, which doesn't really work. So we can measure the centroid of a polygon, which I think also wouldn't really work. No, it doesn't really return any values. But if I take the discontinuities, it gives me 4 points per each branch, which is now fine. Now I don't have to shift path. So I will have one polycurve here, one closed curve here, then I use which is basically just lengths for each one. And then I will take the average, which definitely gives me a point somewhere in the middle. So if you look here, this is a point in the middle of this surface, which is not true, but that's an average of 4 edges. And this one is an average of these 4 edges here. And then I can ask, now I can delete this, of course, and I can ask which one of these 2 points is contained in this bounding box. So to make this really work, I would really like to flatten, but what we can do is we can graft here instead. So I will treat these 2 separately. Now each one is in one branch. Each one of these 2 cut surfaces is in one branch. Now I will have an answer whether one of these is included in the bounding box. The first one is false, the second one is true. So I will keep the one that is true, which is the cull pattern. So this is the pattern. This is what I want to cull, and I will only have the one that is inside of the box. So I will not have this small one. I will only have the bigger one that should be repeated or mirrored. And now finally I can mirror this shape rather than the previous one, and they perfectly match. So this is mirroring with one single surface. Maybe we can try with more surfaces. I will just save this so that we have everything saved, and I can share it afterwards. I will just briefly check the Facebook if you. Okay, the first thing worked. Let's see, what else do we have? Somebody tagged me. Okay. Okay, let's see, what is this? Yeah, it is related. Nevertheless, so you see that this one and this one, this one and this one, these 2 make our symmetry. So I can actually join them, BREP join this one, and I should end up having, not really, let's flatten because that doesn't matter anymore. So I should end up having a single BREP here as the output. It's called open BREP, but I will hide everything. So, okay, I will go through the definition once again to clarify what I've done. So, at the beginning, we have a BREP that we want to that we want to mirror or create some mirrored shape out of that. Then we define a cutting plane or mirroring plane, and we know that we want to cut off anything that is on the wrong side of this plane. This part is only defining the plane, so I can change the shape of the plane, and I can even change the position of the plane. Then I will create a bounding box that is aligned to the cutting plane. This bounding box is though shifted, so it's not really sitting on the plane, it's only aligned to it. And I want to know how far it is from the plane. Therefore, I deconstruct the box into the domains. Now, each one of these contains the domains from where to where the certain dimensions of the box go. And I'm only interested in the z direction, because that's this one, because that's the z or normal direction to the plane. Then I will take the starting value, which actually tells me that that the bounding box is offset minus 59 points this way, and I want to move it back. So I will take the z direction, which is that way. I will take the value from here. I will take a negative because I want to go the opposite. I will create a vector that goes that direction, and I will just move the box here. Now, my shape is not entirely in the box, and that's what I wanted. And I will use the shape to cut off the part that I don't like. For that, I'm using a split brep component. It requires a shape that we are splitting, and then the cutting shape, which is the bounding box. Now I have two surfaces here, and they actually have the same domains. Even if I reparameterize, they still have the same domain because they are trimmed surfaces. And that doesn't allow me to work with them properly. The only thing that I want to know is, I want to take 1 point from that surface, only one, any point, and I want to ask whether it is inside or not of the bounding box. Because if it is inside, that's the part that I'm interested in. If it's not inside, then I'm not interested. So maybe this is a bit too difficult, but I think it works. So I will take the edges, which is curves, then I will join them to make sure that they are not separate edges, but they are basically just one long curve that is made of many curves. So basically now the edges are one curve. I will take the discontinuities, or what I can do is I can divide curve. Also works. So I will divide these curves into several number of items, and I will make an average. Both works. So this is a bit safer. Divide is a bit safer. So the average actually makes 1 point that is mathematically in the middle of the point cloud that I have here. So I have two central points, one for one subsurface and one for another one. Then I will ask whether a B-rep, which is in my case the box, contains one of these 2 points. And the answer is, for one is false, for the other one is true. And I will cull, which means I will remove those that are false, and I only end up having that is inside of the bounding box. So now this is inside of the bounding box. It's not outside. And that's the shape that I want to mirror, and I mirror it around the rotated plane that I have here. And then I simply join the B-reps into one B-rep, and that's one compound surface. Let's see the Facebook. That was private, and there is nothing new here. Okay. So I will also check here. There is nothing in the comments. So let's do this with more surfaces at once, because it might be a bit more complicated because of the grafting and so on. But I think this should be more or less safe. So to make it easy and simple, I will just simply copy this a couple of times here. So 1, 1, 2. Okay, like this. So I've got 3. Let's make it 4. Oh, my mistake. Like that. So I will take these 4, set multiple B-reps, and there we go. So it doesn't really work automatically, because now I have 4 of them, and let's try to graph them, and maybe it works. No, it didn't. So let's see where the problem is. I will hide, no, I will not hide those, but let's see this. If the problem is not really in the position and shape of the plane, but it's not, so it's only working for the first one. So now I have grafted these. I will simplify. So these are the B reps. Now bounding boxes per object, which works well, I believe. Now deconstructing the domains, they have different domains. Maybe we don't have to do it per object, but we can make a union box, but it doesn't really make any difference because we have graphed it. Now, we have moved those, which is correct. Now we split, it still works. This part is good. Now we have the average here. No, it's still working. And now the answer is true, false, true, false. Let's simplify somewhere. Let's simplify here, because I think that we are getting too many branches here. Okay. Again, let's simplify here. Yep, that's good. And there we go. So we are culling, and we end up only having like this. So the problem is here because it tells me that everything is false except the last one. So why is that? We should make sure that these are distributed properly for these. Yes. So now I will show you what the problem is. The bounding boxes are in this fashion. They are distributed into the branches. For each one of these objects, there is one branch, but the points that we are actually evaluating, they have depth of data tree. So there's the first and the second, first and second, first and second, and so on. And this is the problem, because now we are, if we are asking whether something is in the BREP, these two data structures, they don't match. Let's make them match. This is quite easy because we can only use the component shift paths like this. So now we have 2 points in each branch, just like the boxes. So this should work. And it tells me true, false, true, false, true, false. But we basically need to do the same for these. We basically need to do it here. Maybe if I simply don't graft here, yeah, that works. That works. I had to graft when there was only one, but I don't have to graft when there are more. So I should have it. Yeah, no, that was. I need to shift path. We have for each one of these shapes, I have 2 subshapes here if I don't graft, but I end up having the averages grafted because the divide always grafts. So I need to shift path again to get 2 points inside of those, defining the central point of each of the subshapes here. Then I can cull and I will get those that I'm interested in, and then I mirror, and then I join. I end up having a perfect mirrored shape. So if we are looking at something that looks like this, probably this is an NURBS, and this would work. We just have to define the plane here. If this is done, we just can simply cut and offset, and it should work. Let's see if it works. If I move it far away, it still works somehow. There is we need to only make sure that we are interested in this part, not the other one. But you can control it by flipping this plane. If you flip this plane, then you get the other part. So this should work. I think this should be fine for the moment. And let's work with probably more interesting. I will check your messages here. Maybe somebody has some request, maybe not. Just give me a moment, please. Okay, I'm back. Okay. Okay, this is the example. For example, if we start with a triangle or other shape and then start to grow vertically by repeating itself by using anemone, and at the same time we apply some constraints, I can show. I guess I can show an example. Well, yes. Okay. Why not? This is a bit more complex. This is quite easy, but I think this is covered in one of the sessions. You can find this tree-like structure in the session called trees and recursion. Let's see. That was in the iterative made by Mateusz Wierzycki. So I believe that one is perfectly covered here. If we have enough time, I'm going to do that as well. But let's for the moment continue with a symmetry with meshes, which I think is nicer. But we will continue directly with this because that is somehow related, I believe. Yeah, that's Mike Pryor. I thought so. So maybe you should ask Mike. But I'm going to do. I'm going to show you my way of doing these things anyway. I'm pretty sure he has done it differently than I would. But let's give it a try nevertheless. So back to the symmetry. Now I will use parts of this definition. So therefore, I will I will copy it and then freeze one of those, disable. What I'm going to use is the part until the bounding box, maybe even more. So yes, so let's start working with not the bref, but let's start working with some meshes. And this is not a mesh. Maybe you have your own mesh that you want to work with, but I don't. And you can either work with a perfectly smooth mesh, or maybe you want to smoothen the mesh yourself. I recommend the second option. So if you look at the control points here, you see that there is something that looks like a very edgy mesh structure, and it's smoothened out. And that's actually true. That's how the NURBS geometry is actually made. This is called a polygonal hull, and that's an unsmoothened mesh. And then you smoothen it, and you end up having this nicely smoothened out shape. So let's create a mesh using the logic of the NURBS smoothing. So I will take the control points of this, all of these, and you see that one of them should be pretty high above. For some reason, it's not, but nevertheless, it should be fine. Control points like that. Maybe there are different control points here, but I don't think so. No, those are the control points. Yep, that's right. So in each of these, I have 13 control points, which means which is a very strange number. So let's see why that number is like that. I will take this, make this one slightly different. 13 control points for each. That's very strange because that's not a nice number. Yeah, why is that? Why is that? If I take the surface and freeform, match, sweep, surface point in B rep dimensions. Yeah, probably I'm doing it right, but there is some very strange behavior that I don't understand perfectly now. But let's see. We have 1, 2, 3, 4 points in this direction. Then we have 1, 2, 3, 4 points here, and there is nothing in the middle. So it only gives us the points on the edges, and that's probably because that's a curve control point, right? Because that's the that's the edges. So I need to get the points from the shape from the surface, and I probably just need to find that, because surface from points, that's person for boundary surfaces, box elements. Now this is really strange and slightly embarrassing for me, but let's see. Maybe this is what I was looking for. Yes, that's it. So it's called surface points. And it gives a surface, and you see they're perfectly matching with these control points here. So these are actually the points of the polygonal hull, and there are 16 for each one, which works well because it's 4 times 4 control points. Using these 16 points, I can regenerate a mesh. This is going to be slightly messy, but nevertheless, I'm going to do that. So now you see that there are 16 points, and they are not really sorted anyhow. But I'm sure that the first one and the second one are either this one and this one, or this one and this one, or from the other side, from any other edge. Then I know that this one and this one is actually this one plus 4, 1, 2, 3, 4, and this 4. So I can do it like this: item list item, and I will need. Well, that's actually not really the nicest way of doing things. There is something called relative item. Relative item actually takes a point from, or any element from simplifier, from a data tree, which is in our case this one, and it gives you a relative item to it from the same data tree, and you need to define a relative offset. So I will take this. I'm interested in something that is in the same branch. So the branch is 0, and the item is +1, like that. So it should give me 1 point, and then in A, and there should be one that is shifted in B. So it should be this one and this one. And that's already quite good. I need to make sure that I'm not wrapping around in any of these in paths and in indices, because then I don't want to like connect this one with this one. Now I got the first 2 points. Then I need to take this point and connect it to this point, and this point to connect it to this point. So basically I will just take this, and this point would be +1 branch, +0 index. And the third one would be +1 branch, +1 index. If you are not really sure what I'm doing with this, relative, there is a video I made on that in the essentials. I believe it is in the trees here. But to be fair, I need to say that there is a 1 hour long webinar given by David Rutten himself, which you can find somewhere on the internet for free. And he explains the relative items there very, very well. So you don't have to pay for my video. You can go and see the free video made by David Rutten. So now I have, in this A, I have this point. In this B, I have this point. In this B, I have this point. And in this B, I've got this point here. So basically, I got 4 neighboring points, A, B, B, B. here. So this is already something that looks like a face. And because this works for all points one by one, I bet everything is going to work well, and I will end up having a list of faces. So now I'm going to merge them like this, A, B, B, B. And I'm not really sure if this is the correct order. I should probably do it this way. Let's see. And if I graphed here, each one of them, I end up having a data structure that contains vertices for my newly created faces. So now the first number in the data path is which of these shapes I'm working with. The second one is which face, and then the indices are the vertices of those faces. Now let's see if this really works. I will construct a mesh which by default requests 4 points to create the face, and then it requires a quad, so actually 4 points, not 3 points. Let's see, this works nicely, except it doesn't really work. So let's see where the problem might be. I need to make sure that this wrapping is switched off. This is also switched off. Yes. Okay. Now I made a really big mistake here. And the mistake is that I forgot that these branches are not really rows and columns of the points, but they are basically different elements, different geometries here. So this is not really working well. Therefore, what I need to do is I need to change this slight. That slight change would be. I would really like to create a data structure that has the rows and columns separate. So what I should do is I should split those 16 items in each list into a number of views, a number of V's, and they are given here. So I know that I have 4 V's. That's correct. Let's use the thing that the split list, the partition list that I used before. And I think that this time split list would be better. Actually, no, it wouldn't. So what I should do, and in this case, this works well, but let me rebuild one of these to show you that we need to be really careful. So now one of them is going to have 24 items, and the U's and V's are going to be different for each one of these geometries. So the 6 U's and only 4 V's, and therefore I need to know how to split the shape here, the data structure. So let's do the partition list here. And I want to make sure that these points are in rows and columns, so then they are not just packed together. So this should tell me the size of the partitions, and the size of the partitions should be U divided by V. So this divided by this, or actually, no, the length of each of these lists, so 16, 16, 16, 24, divided by the U number, which tells me that now I have, for the first one, I have 4 branches, each one contains 4 points. And for the last one, I have 6 branches, each one contains 4 points. This is probably way too complicated. Maybe I could just do it this way and I would end up having the same thing. Yes, that's true. So this is a division in the U. I'm pretty sure that you've lost me right now, but that's because I'm improvising a bit. Anyway, now I should work with this with this structure, and now my relative paths, they don't work because they only calculate with one level of the data tree, and now I have two. So the first one is defining with which geometry I'm working. The second one is the U, or I don't know if U or V direction, and those four items in each one are points in the V direction. So basically, if I want to define a relative path, for each one I have to say that I want to work only with my geometry, so it should be always a relative offset of 0 here. And I go to the next branch and to the next branch, and this time it should hopefully work, but there is one problem. I don't know what the problem might be, but good. So I don't know, insufficient vertices for a mesh. What is that? There are only two vertices at the end. That's strange. That's really weird. But nevertheless, for me, this looks good enough because it really seems like we are copying everything properly. I believe it's fine. For I don't know what reason this is not really working well, but yeah, I think it's fine. If I do it this way, no, it doesn't work. So yeah. The errors, I don't know what they are caused by, but the result is good. So let's not look for a mistake where everything works fine. I will just check here if everything is good. Let's see. All right. So now I have a lot of mesh faces here. To actually keep those meshes separate like the original ones, I should I should shift paths twice here. So shift paths is removing the last level of the data tree, like this one. So now I have only two levels, and I only want to keep one level. So instead of shifting -1, I should shift -2, like that. And now I have a lot of faces for each one. Ah, I see what's wrong. Never mind, let's keep it anyway. Now I can join those meshes, and I end up having 4 meshes, each one in a separate branch, just like I had the previous surfaces here, or polysurfaces. I will just make a bit more space here, and let's see what we actually have here. So does it look good? I believe it does. So maybe there is something wrong. No, it doesn't seem wrong. It seems okay. Everything seems fine here. So what I can do with this mesh, I can smoothen it. So using the Beaverbirds Catmull-Clark, and they should be very similar to the original NURBS surface, like that. It's not perfect, but maybe we can add one more Catmull-Clark after that, so the subdivision is proper. So the mesh that looks like this, but we don't want to smoothen it just yet. We are going to do it a little later, or actually at the end. Let's work with this really edgy and coarse meshes here. So finally, we've got the mesh. I will save this as broadcast 3, like that. And let's do the same logic. So we need to get the bounding box for each one of them. So now we have the bounding box. We are using the same logic, and we are basically we are moving the bounding boxes like that. Still, it works. Then we need to split, this time not really the original B-rep, but we need to split the meshes. So here I need to change this to split mesh. Mesh split. Split mesh with an infinite plane. So I have the mesh here, and I have the plane here. This is fine. And do I have a nice split here? It seems like I do. So in comparison with the original one here, I have something that is slightly different, and it's cutting everything off. Um, okay, I believe that it's correct, because if I look at that cutting, yeah, so now I'm cutting it properly. What I end up having above and below, and this is so much easier than what we had before, because we can only take those geometries that are either above or below, and we basically know that we want those that are above, or at least I believe. So this is above, and this is below, and we only want to mirror these. This should work fine, and this should be it. So the only thing we do is to mirror and then join meshes. This works, then we are done. It seems like it works. It seems like it works. It creates complex geometries and geometries here. Now we have two meshes. We have two meshes in each branch. We ended up having one. So I can completely delete all the logic here, only because there is this beautiful, beautiful component called mesh split with a plane. If there wasn't, we would have to sort faces and realize which face is inside, which one is outside of the bounding box. But you probably get the idea with sorting those faces already, because we've done that with the B-reps or surfaces. Now we have one mesh here. Before smoothing it out, let's make sure that the mesh is valid. So let's weld vertices. So it's weld, mesh weld. I actually don't know which one I should use. So let's use the Weaverbirds one. So this is mesh join. Weld. So now I just want to check if it reduced number of vertices. It should. No, not really, it didn't. But let's see what another one would do. Weld mesh like that. Okay, this one is better, so I'm not using the Weaverbirds one, so I'm using this weld mesh. It's actually made each one of these one geometry. Then let's unify normals. Normals are each face, actually each vertex, has a vector that is pointing outside of that mesh, and each face is calculating a compound or average normal vector, which you basically use for rendering to know which direction your bump maps should go. Also, you should know where is the inside and where is the outside of the mesh. So I'm unifying the normals only because I want to make sure that everything is fine, and then I can do the capital part smoothing like this, and I can go 3 levels deep, maybe, I don't know. Yeah. And to make this look nicer than it is right now, for some reason this is not welded properly. That's why it makes these things. So maybe let's use another weld. There is one more weld that was here. This is even better. So I'm using this one, and yes, this welded everything properly. And you see that the mesh is pretty nice here. And it also creates complex shapes like this one, because it has some inside and some outside, and it's really quite complex. There might be one little problem here though, and we are going to return to that. But before, I just want to custom preview this. No, custom preview. I want to make it not pink, because by default this is pink. So I will just make it gray like that, and let's see the final shape like that. I'm hiding everything here like this, and this should be visible like that. So this looks pretty fine to me. This one is very nice. I will hide the mesh. So this one looks nice. This one looks nice, and this one looks nice. This one has a little problem. And although I like that this is creating this inside shape here, there is a little problem, and I will show you the problem here. Mesh split like that. So this is the mesh split, and you see that there was this splitting plane we had here. And for some unknown reason, it actually created faces that are touching the plane perfectly here. So we are splitting it here, but still very probably there is an extra face here that was not supposed to be there. I believe it is the case. Yeah, it is the case, because if you look here, there is nothing that would be perfectly aligned with this plane, but it created some extra planes, extra faces here that are touching the plane. And I want to remove those. So let's do one more thing. This is the cut geometry. And I want to explode the mesh here into its faces. And let's do it differently. I will do it here. Explode, and now I have faces that are 11 faces for the first one, 20 faces for the second one, and so on. And I want to ask which one of these faces is perfectly aligned on that cutting plane, and I want to remove those. So what I do is I will now I have mesh faces. I'm curious about the mesh vertices. So it is deconstruct mesh as far as I remember. Construct mesh, I probably mistyped. Construct mesh, yeah. So for each face, it gives me vertices. And now I want to pull those vertices, point to the cutting plane. And if the distance is 0 for all of them, then it means that they are basically laying inside of the plane. And because this is not going to be precise, there is never going to be a perfect 0, but they are going to be super close. So I'm going to ask if the distance is actually, this is the distance. If it's smaller than some value, and I care about all the vertices for each face, so I should put them together with mass addition. And if for 3 or 4 vertices, if I pull all of them and I put together all the distances that I traveled, if that is super short, then very probably I have a problem, and the face is perfectly aligned with that plane, and I want to remove those faces that are perfectly aligned because they create something that is extra, and I don't want that. So I believe that it's these faces here, or maybe this one only. So I will ask whether this is smaller, and let's start with 1.1. I don't, sorry, 1.1. I don't know if this is a good number, but if it is, then one of these faces should be removed. So already I see one that has to be removed, and 2 more, and there are not so many. So it's probably 3 faces that I'm going to remove. But to do the cull, to perform the cull, I need to get a negative pattern. So I need to get a pattern that is that looks like this, and it has to be negative. So what I do is I say gate not. So every true is going to be changed into false and the opposite. And that's the pattern, but it's still not in that very fashion as this one. So I either shift path or unflatten. So we did the shift path before. It basically flattens only the last level. Or I can unflatten this data tree and makes it, if they have the same amount of elements, it simply sorts it into the same fashion. So there is 61 values here, but they are sorted differently. And now they're sorted perfectly like the faces exploded here. And I will call those faces that we touching. And yes, it looks like it removed the proper ones. So now I got rid of that I didn't want to have there. And here I can just take the geometry just like I did before, place it here, mirror, that works, mesh join, that works, well, the vertices, that works, unify normals, yes, Cosmo Clark, and it's all nice now. It works well. Perfect. So I will save this. All the geometries now work well and they look nice, and I think they are correct. Yes. And this is how you can, this is interactive, so I click slightly and you see that it works. It's creating new shapes. So even have these holes here, which I think is super nice. And they're symmetrical. So I don't know if you can hear me again. I will try to share my screen again. Present to everyone. I'm screen sharing and I should be presenting to everyone. So let me somehow know if you can see me and hear me again. It seems on my computer that you can. Yeah. So yeah, there was something wrong with the. I hope you can see and hear me again. So, okay. You can see very well. That's fine. So, I should screen share again. Share. Okay, good. Let me check here. Messages. It's fine. Let me see here. Live control room. All good. Okay. All good. We're back. So I don't remember. I don't know where exactly did we crash. But I said I'm not very sure what Mike was doing here. He's online. We can even ask him, but I wouldn't really as something that I haven't announced before. I think the mathematics behind it. I can show you the cover picture for this event has been made, which is this one. And I have a couple of more of these pictures, but this one is pretty explanatory. So basically what I'm doing here is exactly what I did with the mesh before. But I'm mirroring in random directions only do it. So let's start from this shape that we have here. Let's simplify it a bit. So I will only keep this beautiful one with the hole. So I will delete these two and this one, and it still works. And I will copy this thing here. I will disable, and let's simulate the DLA growth somehow. So the DLA growth, which is described in one of the sessions, I think it was in iterative growth. Yeah, it's this one. Basically, this is a DLA growth. DLA growth is such a growth that you cannot see my screen. Is that true? Oh, I'm sorry. For some reason, this was off. Present to everyone. Uh, 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 uh. Let me know if everything's fine now. If you can see my screen, just let me somehow know. It should be working. Okay, I apologize. Take. Basically, I haven't done anything. I just said that we are going to start from this shape here, this one, and the logic of this geometry, that is the cover picture of this event, is that I took parts of the geometry and I repeated them or mirrored and added to the existing one and let them grow and grow. So I'm not repeating the whole thing, but so because if I repeated the whole thing, it would grow in a grow. So the logic here is the same. We are doing the same thing, but we should do it repetitively. And repetitively, I mean that we need to somehow change the we mirror once, then we select a new plane for mirroring, and then we mirror again, and then select a new plane for mirroring and mirror again, and so on and so on. So to achieve that, I would employ the DLA, which is diffusion limited aggregation. And as I said, when my screen was blank, I'm explaining that logic here in detail. I'll just make it very briefly. So the logic here is that I will take my mesh. So this is the original mesh that I have, this one. I will put it into a bounding box. I will create a bounding sphere out of that bounding box. So I will deconstruct or box properties, like this. Central point of the box, and this is a diagonal. We can use those to create a sphere. So sphere, this is a bounding sphere. Now this is a bit too large, but let's keep it like that. Maybe we can divide this or multiply. Basically, we should multiply it by 0.5 because we only care not about the diagonal, but half of it. But let's make it slightly bigger. So I don't know. I don't know if you. Yeah, so you can hear me, but you probably cannot see me. Yeah, you can see me now. Anyway, again, I don't know where you lost me and what happened. It seems like my internet connection should be much better to actually do these things, but nevertheless, I created some bounding sphere. So basically, I took the bounding box, took the central point and the diagonal, divided by 0.5 here, and create a sphere. I created this sphere because I want to use the DLA. DLA works like this. You create the sphere, you select a random point on that sphere, and you pull the random point to your geometry, and that's where you start growing. And this always makes sure that you're not overlapping or intersecting anything. But basically, I think this should work nicely with our geometry here. The problem with the sphere and grasshopper is that if we select a random point on a sphere, they're much more dense here and much on the sides. So therefore, I would first like to, because it's basically a wrapped surface and it's very dense here and very empty or deserted on the equator. So what I would do also is that I would rotate the sphere randomly so that we don't have the growth only from the top and bottom. Rotate the sphere geometry. This is the central point. Yeah. Maybe I should be back now. Yeah, but also my screen should be on. I hope it is. Basically, well, if you don't see my screen, I will tell you what I'm doing, and then I will go through it once. What I'm doing is I'm rotating the bounding sphere randomly around x-axis and then randomly around, because I don't want to end up having all these. I don't want to end up having all the points on top and bottom. That's basically the reason why I'm doing that. I will check whether, let me know if you can or cannot see me really. For some reason, this is, yeah. Maybe, hopefully you can see me. For some reason, it doesn't really show me the group chat. I don't know. I don't know what you guys are talking about watching my, but I believe that it slows things down even more than they are right now. So, um, so on and off, on and off. What I can do, if this keeps crashing, I will just record the rest of the video and upload it somewhere so that you can watch it. I apologize for this. There is nothing I can do about this very bad internet connection that I have here. Usually it's perfectly fine. Right now it's certainly not. But anyway, so what I've done here, I randomly rotated the bounding sphere. So I end up having a rotated bounding sphere. I will now evaluate the sphere, evaluate surface, the sphere as a surface. I will reparameterize it here, and I will evaluate it at a random position. So the only thing that I'm doing here in this large group of components is that I'm evaluating, finding a random point on a sphere. So I need to get a random u and random v. So basically I can have two values here like that. Two values between 0 and 1. Again, some random seed. Now, list item, I will get the first one, and if I zoom in, I can get also the second one. So I have two random numbers here, and I will create a point, construct point, like that. This is x and this is y, and that's the UV coordinates, and I end up having a random point here. It's really good because I also have a tangent frame here. That works for me. That works for me really well. And I want to pull this point to my geometry. So pull point, this is the point, and the geometry that I want to pull it to is the mesh. So I've got a mesh, which is this one, and I pulled the point here to the geometry, which is this one, this point. So this is my point of growth. If I change this random seed, it's going to be different point where I'm going to. But basically, it's usually on these really exposed places. So, but it can be even here. This doesn't really sound correct to me, but let's do it somewhere here. Yeah. So this is my growth point here. I will just check if everything is good. Yeah, it should be. Now, I'm going to grow from here, but I don't care about the point. What I care about is the frame. So I will just move the existing tangent frame to that position. I apologize. So what I do is I will set a plane origin. an origin. This is my plane. This is my new origin. So now I'm going to grow here in this direction. That sounds good. But also, also, I should somehow go a bit deeper into the shape because I don't want to grow on the outmost point. So I need to somehow cut into, and that's a bit tricky because we need to make some kind of a decision how to really make it. So I would suggest let's see the pulling distance, or maybe let's take the not really the pulling distance, but let's take the this diagonal of the bounding box and let's divide it by a very small number, and that's how much we are going to move it inwards, the plane. So I'm going to take this number and multiply it by 0.1. Here I need to know what is the direction in which I want to go, and it's defined by this normal, which is actually the normal of the frame. I should reverse vector and set the amplitude of the vector to that value, and I should move this plane inwards into my geometry. Now it's cutting through my geometry. That's much better, but even the 0.1 might be a large number, so let's go to 0.05, which is halfway comparing to what we had so far. So this is halfway into the geometry, and that's my new cutting plane. So if I like the cutting plane, then I can perform the cutting just like I did before, which is here. So mesh split. Now this is the cutting frame, cutting plane. I will just put it here, and let's see what happens. Mesh split, and all the way here, Cutmo Clark. That's mesh split, explode. Yeah, it only keeps that part that I want to actually lose, so I want to keep this one. And let's see the mirrored geometry. It looks like this. This looks good to me. And this is the growth that I want to perform over and over again. But I also told you that I don't want to keep growing the whole geometry again and again and make it super big. I just want to take pieces of the geometry and grow only those pieces. So what I want to do here, when I split, explode, I only want to mirror those pieces that are not too far from my cutting plane. So I've got faces here, and I also, I'm going to check if everything is good. Any comments here? Yeah, there is one post here. I would have to think about how to draw the longest and shortest common tangents of multi-circles. I don't know. There is, if you get two circles, there is only one. There are only two common tangents, and they are always equally long. So I don't know. I don't know the answer to this question because I don't really understand. By the way, guys, this was supposed to be a 2 hours long broadcast, and we are 15 minutes until the end of the broadcast. So really, we are not doing any more requests, only if they are super short. Honestly, there's a question that says how to do the CFD simulation in Grasshopper. I don't know what CFD is. I will have to look it up. So I don't even know the answer to this one, and we certainly don't have enough time. This has been announced 2 weeks ago, and I was expecting those questions like in those 2 weeks. And they're coming now 15 minutes to the end, so we are not really covering those questions anymore. I hope you understand. Anyway, so what I was saying, I want to find those faces that are not too far from our cutting plane, because I don't want to copy all of those faces because that would be way too much, because it would grow way too fast. So what we can do is I can, now we have the faces here, we have the vertices of the faces, and we have, we can take the average, which is more or less the central point for each face. And we can measure how far these central points actually are from this cutting plane. So I would pull to that geometry, and I will measure the distances. And I will ask, is the distance smaller than something? And that something has to be something relative. So yet again, I would use the diagonal, just like we did before. And this time, let's say it should be longer, like let's take 15% of that diagonal. And if that fits in, we are keeping it. So if it's farther, we are not keeping it. So if it's smaller, then keep it. If it's not, then cull it. So cull pattern, cull this, pattern is this, and not really cull this. And this has to be, actually, we need to, just a moment. Yeah, we can flatten here. It's not the nicest thing to do, but we can flatten. So only these are within that that distance that I specified. So let's make it bigger. So yeah, 1/3 of the diagonal sounds like a reasonable distance. So I'm only copying this much, and then I will use this here. Again, I will deconstruct and get the vertices, and it should be sorted properly, and I think it is. So this looks good. Now we are only unflatten to this. We are unflattening to this here to make it work, and now we are only making a symmetrical copy of not the entire part, but only of a smaller part. Let's see if that actually works. Cull. Oh yeah. The problem here is we are culling. We should be culling from here. Yeah, like that. And now the output works. Does it? Does it work? I'm joining the mirrored one. So I'm mirroring the geometry, but I also want to keep the original geometry, which is all the way here. So I'm joining this one with this one to actually, and flatten, of course, to actually make sure that I keep the whole original part, and I'm mirroring only a small part. So this is the whole original part, and I put it together with the mirrored part, which is much smaller than the other one. And that actually ends up in this shape. So I can say how much should I mirror. So this is a bit more, even more, and this is the whole thing, and this is less and less. So basically we decided that it should be something around 0.3. That sounds good to me, and we need to put this into some kind of a loop. So now that's the part for the animal. I'm saving this just to make sure. And let's get the animal and let's get the old one so that we see how it's growing. So we basically only need to only specify we need to loop the mesh. So basically into the D0, I'm going to put the mesh. And if you don't know how to use Anemone, just watch one of these videos, one of these iterative videos. So Introduction to Loops in Motion and Growth. They explain everything there. I do. Anyway, so now this is going to be repeated over and over again. I end up having some kind of a mesh here with unified normals, and that's the one that I want to loop back and use the output here. So to actually achieve different random values for each repetition, we should use the C as a random, this is the counter, we should use it as a random seed, but to make sure that we really have values, I'm just going to multiply the C counter with these sliders to actually get perfectly random seeds. They're not perfectly random anyway, but they are slightly better. So there are 3 randoms, connect them to the C, and let's make 5 repetitions and see what happens. Save, because maybe it crashes, and let's see what happens here. There is an error here for some reason or another. Let's double click to restart. Yeah, there is a problem. So let's see where the problem might be. So 0. We have the, I'm going to hide everything because I want to see what is happening. Whoa. So this is the shape that we are repeating. That's pretty crazy. Just making sure everything's fine. And it looks like this, but it looks good to me. So I can hide this. I can hide this. I can hide, there's something still visible. I don't know what. Oh yeah, this. So the first one was okay. Now the second step, still okay. We are only repeating parts of the shape, parts of the geometry. The third one, and there is a problem. So what seems to be the problem? Oh yeah, there seems to be nothing below. So what is the shape? This is the shape. We get this here, and if we chop it, there is nothing here, and there is everything. Oh, that's empty. So this is not performing at all. So this might happen. I don't know why this is happening, but we can just prevent it. Prevent this from happening. This mesh split for some reason doesn't work in this case. And we want to do something about that. It doesn't work. So what we can do is we can check if this actually contains something. So I'll measure the length, or if this is 0, this is 0, and in this case it tells me it's true. So it contains 0 values. Then I have to pick and choose. If this is 0, then if this is true, if this is empty, then I will loop back the original mesh and try with the new values. I'll try to do it with the new values. But if I'm wrong, and if everything's fine, then I will take the newly created mesh and I will loop back that new mesh. And let's see what this little component can do for us. So right now, it only continues or only works with those meshes that are actually correct. And it seems like it somehow works. It's getting really crazy now, but it is somehow working, and it's growing, and it's creating structures that I would never imagine before. Let's see. So now it's growing like this. And we can keep growing much more. And we'll somehow reduce this distance. And we don't have to do it only 8 times, we can do it 100 times, which sounds like not a good idea because it's going to be super big. But you see that now it is somehow growing, and somehow we are losing parts of it because it's not always perfect, because all these cutting and all these methods, I will just pull this down because now it's getting really heavy. So whenever you do some sort of cutting, splitting, intersections with Rhino and Grasshopper, very often you might get an error, and that's not what you want to do. And but basically, you see that this one somehow works. It creates shapes. It creates certain shapes, and these shapes, I believe you can do something out of them. And also, it all depends on the mesh that you're using at the beginning. You can even import any stock mesh. You don't have to create it the difficult way as I did. Just make sure that it's not really smoothened, because that doesn't look so nice. And this actually works well. Although the geometry might not be perfectly valid, but the logic that I presented to you here is exactly the one that I used to create these shapes that we had that I used for the teaser for this event. So let me just show you the renderings that I made before. So it's this one, and at the end, but you see that there are gaps, there are pipes. It creates really nice shapes. Maybe I should go the other way. Yeah, this is another shape. This is another one. This is how it looks if you set it properly. So maybe right now all the numbers are not well set, but the logic is good. It works well. I will save it, and that's broadcast 3 right now. And I have a message here. So if you have time, can you walk through what you did, starting from the sphere bounding box? That's when the connection was cutting off, or maybe you have time. I understand if you don't. So yeah, I have that much time. I can do that. Let's see. There is one more post here. Yeah, once again, if this question was posted yesterday, then we would do it. Sorry, we cannot really do it now when we are 3 minutes to the end of the session. So please, next time, you're perfectly welcome to ask your questions. You have to do it before the end of the session or before the session. So once again, what we are doing from the bounding sphere. So basically now we are in a loop. And the loop is actually creating a diffusion limited aggregation. So the diffusion limited aggregation works like this. We need to have a sphere that is bigger than your entire geometry, which is this one. And you select a random point on the sphere, which I'm doing here. This is the random point on the sphere. And also I care about the plane. The thing is that because of the way Rhino and Grasshopper works, this is never perfectly random. And therefore, I'm rotating the sphere as well to actually achieve a better randomness. So that's why I'm rotating twice, to actually rotate the sphere first and then select a random point. If you pull this random point to your existing geometry, which in our case right now looks like this, so if I pull it here, then I will find the outermost point of the whole geometry, which is actually very good because we don't want to grow somewhere inside. We don't want we don't want any overlappings to happen. So if this is if that's the point where we start to grow, you're making sure that you're growing only outwards and your structure is never growing inwards. Then I pull the point to the geometry. I will change the origin of the plane. So I actually pull the plane there. That's my cutting plane. But I also move it slightly inwards. And maybe this is even too much. I should move it slightly less inwards because I'm chopping off whatever is outside and like that. So that if the outermost point is a tip of the geometry, we don't want the geometry to grow from the tip. We want to grow it from the flesh, actually. So that's how I grow here. So that's my chopping plane. Then I chop the existing plane. I split it with a existing geometry. I chop it with a plane, and I get something that is that should be the repeated or mirrored part. I just need to make sure that there is something inside. This is just telling me if this is 0, then use the previous one. If the number of geometries here is 0, then just ignore this step and go to the next one. Use the original geometry. Otherwise, use the newly created one. And how do I create the new one? I just chop everything into faces. Then I find into faces. So I take the face. Actually, I could. No, there is. No. That's correct. So I take the vertices of each of the face. I will find the center of each of the face, and I will pull the face to the construction plane. And I only care about those that are close enough to the cutting or mirroring plane. Maybe this is not a good idea. Maybe I should go and pull it to the point itself so that we are not growing the whole structure all the time. So let's even try that. Now I will deconstruct plane. And instead of pulling it to the plane itself, I will pull it only to the origin. So now I will cull off everything that is too far from that growing point, and I will grow only the close geometry, which is, in this case, it's this one. So it's a sphere around that growing point. Then I deconstruct the mesh again, and I again pull all the points to the construction, to the cutting plane. What do I do then? I will, I'm removing those. Yeah, this is the thing. Sometimes when you do this cutting, what happens is that it creates faces that are touching the construction plane perfectly, and they are just copies of the construction plane. And we want to get rid of those. So if I pull the vertices of each face to the plane, and I actually end up having the distance that I pulled altogether very, very small, it means that I'm basically having a face that is perfectly aligned and touching the plane, and I don't want to have that one because that is not nicely mirrored. It's like if you're mirroring something that is touching the mirror. So I'm just removing everything here that is touching the plane, a cull, and then I know that the remaining part I can mirror, and I jump to the rest of the structure that I have. I just weld it, unify, and put it back to the loop, and I do this many times over and over again. So right now, let's see what happens if I change when I change the logic slightly. The logic now, actually, I really don't like how does it look right now. So I will start not from 0, but I will start from some number. I don't like the first random point that we got. So once again, what do we get here? Let's make the repetitions like this, and this is the result. I don't know if it's correct, but it seems like it works for some reason. And it's creating mirrored parts of the mesh, and also the topology is somehow interesting. Yeah, I think it's fine. It works well. One thing that we can do, we can add some thickness to it before smoothing it out. So before the Catmull-Clark, which is at the very end, we can go thicken, Weaver-Bird mesh thicken, which is this. And we need to also specify correct thickness for that because by default it's set to 5. In my case, even 10 or 11 could be okay. So let's see, what does it do? Yeah, 11 is fine, even maybe around 20 would still look good. So now I have a thickness at that mesh, and I think it looks quite interesting. And everything is made by mirroring. And yeah, these are some mistakes, but I don't know how did they happen, and they look kind of interesting, I have to say. This is not a perfect definition because there are so many things that can go wrong randomly, and we can't really handle all of them in such a brief session. But if you play around with it and try to figure out how to, when does such a mistake happen and how to avoid it, then I think you're going to be good. The mesh geometry modelers, what they usually do is when they use the weld, just like we do here, there is certain tolerance. And I see there is one, so let's increase the tolerance to, I don't know, let's say 5.0, which actually welds all the points that are close enough to each other. How does it look at the end? Well, it doesn't really look so good. So when the problem is that this Weaver-Bird Catmull-Clark is very picky, and it only accepts a nice, good geometry, and this one is certainly not the one for some reason. And for some reason, it cannot be even displayed. So maybe welding them too much is not a good idea, but now it seems to work. So let's see. Welding too many points together probably breaks the geometry, but I don't know. So you can play around with that. You can play around and figure out when these things happen and what they actually are. Maybe they are not mistakes. Maybe they are correct. Maybe it's because of the shape of that we started from, because we still started from this shape. So if I change the shape now, it will even influence the whole growth. And you see that it looks better now, very different, but it all has started from that original surface that we had here. Okay, there are still not so many people watching. I mean, not so many people are watching it live, but I will make this available online. And it seemed like it crashed, but maybe not. I think I'll just reduce the number of repetitions to something like 20. And let's see what happens. I got a message. I need to check it. Oh, yeah. Yeah, I'm going to do it. I think it's been recorded. I think it's been recorded by the YouTube, because these Hangouts, they work through YouTube. If it is recorded, then you're going to have it either on YouTube or through the main website of the Grasshopper sessions or the research sessions. I think I will put it here. It will still be available for free.